All right, so we're finished with the energy transfer of the block of aluminum in the water. Now I want to talk about energy transfer. This is not in the notes, um, but I want you to watch through this and take a quick look, because if you flip over the back of that page from the notes, you're going to see, or you scroll down to the next page of the notes, what you're going to see is an acrylic testing box. That is what our project is going to be focused around, that thing right there. So we're going to do something very, very similar to that here in this example. And then we're going to do that for real on the insulation materials that you create. So we're going to calculate energy transfer in a section of wall that measures 2 meters by 1 meters, and it is 0.04 meters thick. It has a thermal conductivity of 0.10. Again, thermal conductivity is something we will give you. We will tell you that that's a constant number. Opposing sides of the wall section have a temperature of 10 degrees Celsius and 5 degrees Celsius after 1 hour. So we have a whole bunch of things in here that we, same situation as last time. You write what you know, you write what you don't know, you pick the right formulas, and you kind of like plug and chug them away. It's a little tricky because sometimes you have to rearrange and combine formulas and stuff like that, but here we are. List all the known things. The area of thermal conductivity is the area of the wall. It's 2 by 1. Okay? So 2 square meters. Thermal conductivity we gave you, it's 0.10. Thickness of the material is 0.04 meters. And the difference in temperature here, we have 5 degrees. Looks like delta T of 5 degrees. So 10 minus 5 would be 5 degrees. The last thing here is change in time. And if I can get this stupid slide thing to disappear. Here we go. 1 hour. Now we have to do this in seconds, so we have to convert hour 1 hour into seconds, so it's 3,600 seconds. All right, so here we are. Oh, my keyboard isn't working. List all the unknown values. Okay, we don't know the energy transferred, and we don't know the rate that the energy was transferred at. Okay, so those two things are pretty important. The amount of energy transferred, obviously, if we're dealing with something that's insulating, we want that rate to be low, and we want that energy transfer to be low, and we want the rate at which it happens to be a very long time. Okay, the more insulated a material is, or a space is inside of a building, the better numbers you're going to have here. So we're going to select our equations. This is back a couple of pages in the notes here. We had these two equations right here. P is the rate of energy transfer, Q and delta T. Q is the energy transfer, delta small t is time. And then the one over here on the right, we have, again, a rate of energy transfer. K is our thermal conductivity, area, and then change in temperature, and then L is our thickness. Okay, so we're going to solve in terms of Q. First, we want to find the energy transfer. We just basically took this formula and rearranged it. And if you take a look, you can see in this formula right here is a P. Q equals P times delta T, small t, time. If we take this entire formula right here and plug it in right there where the P is, we now have a new equation that we can use to solve this problem. Okay, so all I did here to find this equation on the bottom is not going to be on your, this one right here is not going to be on your formula sheet, because we just combined it in this slide. Okay, so I'm taking that formula that we just made up by combining, and I'm going to substitute the values that I know in there. There we go. K is my thermal conductivity. That's my area. That's my change in temperature. Make sure you don't mix those two up, all right? The big T is temperature, the small t is time. Divided by my thickness, and multiply all that by my time, and I come up with 90,000 joules, okay, of my energy transfer. That's my energy transfer during the 1 hour of time, okay? Stop here for video 2. Yeah, because we're not doing coefficients of heat conductivity yet. So that's that. We are going to do something very similar to this right here that you just watched when you create your thermal insulation, renewable insulation material. All right, so I will see you then when we do that.